Hey, welcome back. So today we are back with another implementation of our simple text adventure game in a vintage programming language. And today's programming language is Turbo Prolog 2.0. So why Prolog? So we have messed already with some imperative language like C or BASIC. And I want to look into functional programming language, so more specifically Lisp. But I know some things about this language already, and I was not really familiar with logic programming, which is the kind of programming that we do with Prolog, which is sort of a declarative type of programming rather than imperative or functional. So yeah, it seemed like a very good opportunity to learn something new, to pass. So I try to learn a bit of Prolog, enough to put together a simple text adventure and share with you. So if you are an experienced Prolog programmer and you see anything funny going on here, please let me know. I would love to learn and share with the audience. And why Turbo Prolog? So Prolog was never much of a commercial success in the past 10 or 20 years. It's, of course, it is a language of historical importance and is used in export systems, is used in certain niches. And the currently favored flavor of Prolog, I believe it's something called SWI Prolog. But back in the 80s, Borland acquired from a smaller company this product, an integrated development environment for Prolog and the corresponding library and language, which they branded Turbo Prolog 2.0. And it came out, if I'm not mistaken, in 1986 for the IBM PC. And it was kind of a hit back then. I remember as a kid, I got a chance to look at this program that asked you questions. Actually, it asked you first to imagine an animal, right? So you could come up with, I don't know, a duck or a lion, and or a platypus if you were feeling like giving a hard time for the program. And then it started asking you questions like, does it fly? Does it have fur? And so on. And you answered those questions, and eventually the program would take a guess at what animal you had thought, and it was often correct, more often than not. So that was quite a surprise to me. I was really really excited with that as a kid. And now I realize that that program must have been written with Prolog in the second half of the 80s. So let's take a look at what it was programming a text adventure with Turbo Prolog 2.0 in an IBM PC around 1986, 1987. Let's go. Before we get into the game itself, I want to introduce you to Prolog, and more specifically to Turbo Prolog. So Turbo Prolog 2.0, the development environment that we are using for this video, is a Prolog version sold by Borland in the 1980s. It evolved into a product that today is called Visual Prolog. And today the most used version is SWI Prolog, which is a different product. But in this video we are going to use this vintage Prolog, which is actually a bit more complicated than the flavors that we have today. So everything that I show you here, if you use a more modern version of Prolog, it's going to be actually simpler. Oh, that's good news. So I'm running this in DOSBox, and I have Turbo Prolog installed, and on the GitHub repo with the code that you can find on the video notes, I will also explain how you can build an environment like this. So Turbo Prolog, you have to use the keyboard. There is no mouse. And also you do not have undo, you do not have very, things that we consider basic these days. but that's what we have. So I start with a new file and Prolog. So a logic programming language is quite different from BASIC or C, like we used in other videos, imperative language. A logic programming language, you don't give a set of instructions in order for the computer to execute. What you do is you give the computer a set of facts or beliefs, and then based on those beliefs or facts that make up your knowledge base, you can query, you can ask questions, you can make queries that are going to answer you based on that knowledge base. So you kind of teach things to the computer, and then you ask questions to the computer, who can in turn answer based on what you taught it. It's easier to show than to talk abstractly, so let's go for an example. So classic example when talking about formal logic is to say every man is mortal, and then now we can say something like Socrates is a man, and then we can ask the question, is Socrates mortal? And the computer should be able to tell us that yes, right? Because if Socrates is a man, or it's human, better to put it this way, if Socrates is human and every human is mortal, then logically Socrates is also mortal. But how do we say that in Prolog? So every human is mortal. You could think in the lines of if you have a human called X, that implies that X is mortal. Right? Given X, if X is a human, then X is mortal. And in Prolog, we kind of flip this. So we start by the conclusion. We say that X is mortal if X is human. So this arrow is sort of inverted, and we use a different character for it. So we say something like this. If you have a mortal X, that means that X is mortal if X is human. So it's basically we are flipping this the order. We are putting the arrow on this way, and then the arrow is actually typed like this. And then we say something like this to say that this is a predicate, right? So being mortal is a predicate of X if being human is a predicate of X. So this is how we say every human is mortal. And then we say, by the way, I forgot, we have to put a period at the end. So, and here that's when we say, okay, Socrates is human. So these are the two facts that we have in our knowledge base. So if you were running this in a more modern version of Prolog, that would just work. But Turbo Prolog is a older, fussier, and typed version of Prolog. So we have to add some more syntax here so that we can run this thing. But by the way, if we try to run it now without R, it complains that mortal is an illegal keyword because basically it does not recognize it because we have not declared it in advance, which now we should do. So we do this by having a predicates section here.
where we say that we have two predicates. The order is not really relevant. So we say that we have the predicate human and we have the predicate mortal, and that both take one parameter, and that parameter is a symbol. And a symbol in Turbo Prolog is just something that's uniquely identified by that that symbol. So if we say that Socrates is a symbol, that Socrates stands for one individual named Socrates, and every time we refer to Socrates, we are talking about that same instantiation or individual or variable, depending on how you see it. And now these two things that we have here, the sort of the knowledge base, I'll delete these comments. This must be in a section called clauses, because those are, for Prolog, those are called clauses. So the facts or beliefs that you provide are clauses. And now let's run this. And you see that we have now a blinking cursor in this other window called dialog. And this is the interactive window that we use now to query our base. So the question that we can ask here, the question that we want to know is Socrates mortal? Yes, he is. So here's the logical inference happening. And now we can ask other things like, is Plato mortal? And it answers no, because it doesn't know Plato. So, right, Plato could be, I don't know, the name of a god. And now, the god is not mortal. But in our case, we know that Plato is human. So we can come here and add this information to our knowledge base. We can say, okay, Plato is also human. And now we run this and we ask the same question again. And now it gives us an interesting answer. And also we can ask something like, what are the x where x is human? And then it's going to tell that in our case, there's two symbols that satisfy this condition, that have the human predicate, and those are Socrates and Plato. Last two things we can explain here about the syntax of Turbo Prolog is you can actually define sort of named variables in a sense, or you can create categories of symbols. And this is called domains. So for instance, we can say that there are names, and name is a symbol. And now we just can refer this to as names. But that ultimately is not going to change what we had before. It's just an alternative that we have. So if we want to give meaningful names to the symbols, and there's other types of variables, we're going to see this. There's like strings and other things we can use, lists. And they are all defined here in the domains section. And finally, you see that when I run this, I get to that dialog, right? Nothing runs automatically. But we could say that the goal of this program is to answer the question if Socrates is mortal. The goal section. And you see that now I have executed, it just immediately executed my question. And now I can go and press the spacebar and get out of it again. So this makes my goal to be automatically executed. So this is a very, very simple example of how we do stuff in Prolog. And now we're going to switch to programming our text adventure. And in the process, we're going to learn much more about how to think in Prolog. So to get started on our game, let's start with a new file, with a clean slate. And this text adventure game will have 4 rooms or 4 locations that you can move. And they are an empty office and something we call the stock room, the dark room, and then the world outside. And you win the game by getting to the world outside. So those are kind of basic facts of our game world. So we have to start in Prolog identifying those facts. So let's say that we have a predicate. Called room. And we basically say that something is a room or is a location in our game. And to make it easier to read and understand, let's call, the things that can be a room, they are a location. So you have a symbol that is of the location type, and then it can have the predicate that it is a room. And now we have to define some clauses. And we say that we have a room that's identified by the symbol empty office. You cannot use dashes, but you are allowed to use underscore. So, okay, we defined, let me save this, the name work.pro as in Prolog. Okay, now let's run it. So I can ask, is the empty office a room? Yes, it is a room. Is the, I don't know, the playground a room? No, it is not. We don't know no playground. So that's the bare foundation of our game. Of course, we want to be able to print out to the user a description of these rooms and also indicate where we are. So the part of explaining where we are, it's easy. We create a new predicate that applies to a single argument, that's a location. And we apply the predicate here to the location that we are. There will be only one. And we start in the empty office. So the predicate here applies to the empty office when we begin the game. So if we run this, we can check which is the X that is here, and only the empty office satisfies that condition. But if we ask which are all the X that satisfy the condition of being a room, we have 4 of them. Okay, now on to the description. So for the description, we're gonna have a new type of predicate, one that takes a location and a string. So this predicate is basically going to associate a location with a string with the relationship description. So we declare that the predicate description applies to a combination of the empty office and a string you are in an empty office. Then later we're gonna make this description a bit more colorful, but for now let's just make a simple one. And stock room, you are in a stock room. And then for the dark room, okay, so right now if we run this and we say what is the description of the empty office, yeah, I'm sorry, we have to do something different, so ignore this example. So what we need to do now is to define a new predicate that's called print location, and actually, or we could call it look, because we're gonna look outside, look around us and describe where we are. And it will not take any argument. So I'll just leave it without any parentheses about without anything. So we say that the predicate look implies that you have a location, and that location has the predicate here. So this is same thing as saying here X, and you remember that this gives you all this, I mean the empty office, because that's the only place where you are. So X is going to be the empty office, but I'm gonna give it a more descriptive name. So this is a variable, and all variables, they start with a capital letter in Prolog. So a variable called location, and this variable will satisfy the predicate here, being here. And there's only one that satisfies it. And then I say, okay, I also want the condition to hold true that the description of this location, so we know the location here is the empty office, so the only description out of the 4 descriptions that will match the condition of having the location that has the predicate here is going to be the empty office. So we're gonna have a location and a description. And now we are going to do something funny. We will call a clause that is, or a predicate that is made available by the Turbo Prolog language itself. So we have not declared this predicate anywhere, because we are already given it, and you can figure out all the predicates that you have in the Prolog library that you can use by checking the documentation, because that's how we did it in the 80s. I can point you to some books that you can find online that will explain all of them. But we're gonna call a predicate called write. In this predicate, you pass a string to it, and this predicate always returns true. I mean, always returns yes, it is always successful. So we don't really care what is the answer, that the answer is like true, it's yes. What we care is that this predicate has a side effect. And the side effect, as you guessed it, is to print on the screen the string that we provided here. And I will end this by calling the predicate NL, or new line, without passing any argument, which again always returns success and has the side effect of printing an end of line to the screen. So here, when we call the predicate look, it basically queries for a location that satisfies the predicate here, and then a combination of location and description where the location matches the same location that has the predicate here. And then we write to the screen, you are in the description that was part of this relationship. So this is how we think about this. And if I run this now, I see it prints, you are in an empty office. And if we were to come here and change our facts a bit and say that we are actually, here is the dark room and not the empty office, and then we run it, we see the difference. So here's how we print to the screen and how we print where we are currently in our game. Of course, the next question is, how do you move now, right? How do you go from one room to another? And that's the question that we need to answer by extending a bit our program. First, we need to know where to go, right? So if I try to leave my current room in a certain direction, let's say I am in the empty office, that's where I start, and I want to go south, that will take me to the stock room. So somehow I need to put in our knowledge base the information that if you leave the empty office room going south, you end up in the stock room. I will add a new predicate called exit from to. So we're gonna have three arguments here. We say the location we are coming from, right? So that would be the empty office. And then we have a symbol of the direction. And then we go somewhere, which is another location. So this is exit from to, the way you read this, like from this location through this direction, I arrive at that location. And again, the order is not that important, but you must put all the predicates, all the clauses using the same predicate. You need to put them one beneath the other, like this description. All the four of them are together. You cannot put like another description somewhere else, but that's a detail. And now we say in our clauses section that you have an exit from the empty office. And the direction is south. And you land in the stockroom. Actually, you don't need this. This is sufficient. So if you leave the empty office in the direction south, you land in the stockroom. And actually, the opposite is also true. So if your origin is the stockroom, and you go north, you're back in the empty office. Because you have a connecting door, you can go one way or another. So we check here, for instance, if we have an exit from to, and then we are leaving from the empty office, and we have a direction and to location, I'll call it 2. So there's only one solution, and that solution is if you are going out from the empty office right now, the only thing you can do is go south to the stockroom. So now we know how to connect things, but still, I mean, we haven't changed this. I mean, the fact that you start in the empty office. And to do that, we need to be able to dynamically change this predicate, right? The change what satisfy this predicate, that the empty office has the predicate here, because I mean, if we move to the stockroom, then the stockroom we're gonna have this predicate and the empty office will not have it anymore. So the way that you do it is you input a new section called database, and the database really contains the predicates that are changeable. So all the predicates that you have on the section predicates, once you make statements or you declare facts using those predicates, you cannot retract them. You cannot say, oh, wait, this is not true anymore. But you have it in the database section, then you can do it. So there are other ways that we could build our program, that we could accomplish the same thing without having any changes of facts. But because this is a feature that often we use in Prolog, for me feels like the most natural way to do it, at least for this example. So we're gonna move this predicate, that the location, the here predicate, we're gonna move to the database section, so it becomes changeable. So we cannot copy and paste. This is really primitive, so I have to retype it. But okay, it's here now, which means that, I mean, this clause is still holds true when we start the program, but it can change. And the way we change it is by using other predicates that are given to us in the Prolog library, that you can retract a previous clause. So we're gonna create a predicate, a clause that we are moving to X, right? So X is going to be our new destination. And that implies that we retract that here is the empty office. However, I mean, this will work the first time I run this, right? Because I'm retracting the statement that here is the empty office. But if now I change the statement to say that here is the darkroom, and then I'm running this move thing again, it will try to retract that here is the empty office, but that condition will not exist, so there's nothing to retract. So this should be anything. So we are retracting that here, that anything is here. However, if we give a named variable, like this X is the name of a variable, if we give a named variable, we have to use it somewhere in the Prolog program. If we do not want to use this variable, we just want, you know, whatever the hell that has the predicate here to be retracted, and we don't do anything with the result, we have, instead of using a named variable, we have to use the anonymous variable. So the underscore is the anonymous variable. It means just something that I don't care what it is. So we are retracting that the here predicate applies to anything. This will find the first clause that states anything about the here predicate, and we'll retract it. So if we had declared, for instance, if we do a retract of a description, which we're not doing right now, but if we did that and that applied to 4 descriptions, we would have to use another predicate called retract all. But in our case, because the predicate here, there's only one place that is here, so we can just retract. It will retract the first one, and the first will be the only one, so that's fine. So we retract that here is wherever here it is now. But we also now we assert, and asserting is the opposite of retracting. So assert, we are stating a dynamic fact. We are asserting that here is now X. Because X, you can see, is the place we are moving to. So we could also call it 2. So we retract that there was ever a here, and now we say that here is the new destination. But that is not enough. So, I mean, this will work, and we can probably see it. Oh, of course we have to declare the move predicate. This one, I mean, is not a predicate that we are changing. It changes something else, but it itself doesn't change. So we're just moving to a location. So now, if I look, I started the empty office, but I could do something like move and move to the, I don't know, to the dark room. And now if I look, I am in a dark room. So that worked. So, but what we want is not to just say move to this symbol. We actually want to say go in a certain direction. And if it's possible to go in that direction, then we want to go there. So we shall add a new predicate called go to. And we go to a certain direction, right? And our direction in this case, it's a symbol. So you go to a certain direction. And if it's possible to go in that direction, we should move to the corresponding room. So we say, I want to go to a direction. And that implies that there is a location from, which is our origin, right? That's where we are right now. That has a predicate here. And there is an exit from the location from that goes in the direction, right? So if we said go to south, then the direction here will be south. And there will be a to destination, right? So there's like this tuple with three things tied together. A room you're coming from, the direction you're going to, and the room that you end. And if those conditions are satisfied, so I am here, and from here there is an exit in the direction I want to go, then I move. And then I move, of course, to the location 2. What happens if these conditions are not satisfied? So every time you run a Prolog program and you make a query, it will go and check the knowledge base and try to find a match. So if we go in the direction south, it will find a match. We are going out the empty office and going south, we will find a match. But if we say, let's say, go north from the empty office, there's nothing north of the empty office. So this condition would not be satisfied. We will not find this exit from to predicate, right? We'll not find this clause here. So what we do then is we provide another go to clause, because if it tries the first one and finds it, right, you have an exit that direction, that the first one is going to be a match, it's going to satisfy, so it will stop searching. It will not go and try the next one. However, if we are going in a direction and it really doesn't matter which one, if we got here, there's no exit. So we want the result of go to be that I inform the user that you can't go in this direction. And we could here say that this succeeded, right? It succeeded in informing you that you cannot go in this direction, but I think it makes more sense from a semantic perspective that we say that this is failing. So we failed to go to. So this is going to answer no You see that we called those goals, and we got an yes because it succeeded. And in our case, I mean, we're still gonna do all these things. We're gonna write, you cannot go in this direction, but then you're gonna say that's a failed condition. And this actually becomes more important later. This is related with how we control flow of execution. First, I want to show you that this works, and after that, I want to show you briefly why this works, or how this works. So we are in the empty office. Then we say, I want to go to south. And then I look again, and I am in the stock room, right? And now if I go to north, and you see that succeeded because it means the first condition was satisfied. So this first clause here of the predicate go to already succeeded, so it stops going for the next ones. But if I say go to north again, because let me show you, I am in the empty office. So, and there's nothing north of the empty office. So now if I say go to north, I get that you can go in this direction, and we have the no because it failed. So what happened here is that it tried to find a match, it couldn't, then it went for the next one. And here, because anything will match, then it matched, but ended up with a fail because we said so. And if we want to look at this happening, we can do something here. We can put a short trace or trace. I mean, you have a trace, which is very verbose, and you have a short trace, which is slightly less verbose. So we can kind of debug our little program. So let me show you this in action. So if I put look, you see it starts calling the look predicate without any arguments. And now I hit F10 and it steps in. So this is the clause that we land. And then it's going to try to find the clause that where we have a location that matches the predicate here. And you see that it found saying that's the empty office. So that was the return. And now we try to find a pair of description, location description, where the location is the empty office. And we find it's the first attempt. You see that it's going to try, and it found it in the first one, and then it returned successfully. So now we have, we kind of bound the location and description variables to the results of those queries. And now we write on the screen what we want to write. And that finishes the look predicate, and we are back to our goal. So now let's do the go to south thingy. Again, F10, we step. So we landed on this first clause where we try to find if we are here, and here is the empty office, an exit that goes south. So this is the first attempt, empty office, direction south. It will be a match. So we are back here. And now we go into the move. And the move, we retract that here is the empty office. And you see that down here it's saying it's retracting that here is the empty office. And now it is asserting that here is the stockroom. And it ends. So now if we try to go south again, which does not exist, right? Because there's no rooms south of the stockroom. We try that. It will try our first clause, but now we will not find anything. So here is the stockroom, and now it tries to find a combination where from the stockroom you can go south. So it will try the first one, empty office, doesn't match the stockroom, so this one is not a match. Now we try the next one. This matches the stockroom, but it doesn't match the direction because we can only go north. We don't have anything south. So it failed to find this, which means that now we go to that next condition, right? We go to the next clause. We only got here because we failed to match the first one. which was the case when we had a valid room connection, but now we don't. Then we end up here, and the fail thingy is giving me this no here. So let me remove this trace because otherwise it's quite verbose. And then we go to our next step. And our next step is adding objects to our world and putting these objects in the rooms, and later describing what objects are currently in the room. And the way we do that is actually a lot of more of the same. There's only one kind of new thing I want to show you, but now I will not waste your time watching me type slowly. And so I have already pre-typed everything. We have a number of new predicates here. For instance, I have changed a bit our description, because before it was connecting a location with the description, and now it's just a symbol with a string, because we are reusing these not only for locations but also for objects. And then we have some predicates to take an object, to drop an object, to list the objects that are with the player. And by the way, also have used kind of a dirty trick here. And that dirty trick is that I have now a fifth room. That's a room that you're never gonna land there. It doesn't even have a description because nothing connects to it, but that's the inventory. So when you take an object, I can say now it's in the inventory room, in the inventory location. And when you drop it, it goes from the inventory location back to a room location. And you can see that our database now has not only the here, but also the location of a certain object, right? So it's a word, the word is just the name of the object. So you give a name of the object and its location, and we're going to change the location using retracts and assert clauses, like we did for changing the here predicate. So this now we have this fifth room, and now we have some new predicates here. We have two objects, that's a lamp and a key. So the lamp is sitting in the empty office and the key is in the stockroom. So that's what we say here, say the location of these objects. And now the description, we have the description of the locations or the rooms, but also of the objects. And you see I moved all the descriptions together because they have to be one, I mean they must be all bundled together for Turbo Prolog. And here the look predicate has a new thing, which is you see, and then we're gonna list the things that you see in this room. And this is the new thing I want to show you. So we have a predicate named list things. So it's supposed to list more than one thing, assuming that there's more than one thing in this location. And we start by first checking if there is a thing that is in the location that you are listing. So if you're listing things that are here, so the location that is here is going to be the one here. And the inventory also, we pass the inventory as the location. So yeah. We say this, I want to list things on this location, and then we are saying, okay, for a thing that is located on this location, so there may be more than one, but right now we are matching the first one. I take the description of the thing, so I find a description where thing is the first element of this tuple, and the second one is a description, so this will be the description of the thing that is in the location, the same thing. And then we write just a tab character, so we ident this a little bit to the side that we want. And then we write the description of the thing. So basically, if you have, for instance, in this location, you have lamp, you're gonna print tab and then a lamp. and then you print the new line character, and that so far it's all, I mean, it's all familiar stuff. We have seen this in the previous examples, but here we have a fail. And why do we have this fail if we actually had a match, right? We got here, we found a thing that is in our location and we print it out, but now we are failing. And the reason we do that, it's because if we succeed, right? So if we have a match, we saw that Prolog is going to stop here. You're going to say, okay, I have a match for this clause, so I can move on. But this fail will actually tell Prolog that although we had the side effects that we wanted, right? We printed out the name of the thing. The fail is going to say, this is not a match. And because this is not a match, this will make Prolog to try to find the next thing that is on our location. And then it will print out this thing, and then it's going to fail again, and we'll keep failing. So at some point it has to succeed, so it moves to the next thing that needs to happen. And that's why we provide a list things that just has, I mean, whatever location you pass, it will just return with success, but without any side effects, and without you do nothing, you just return an okay. So you actually come here and you keep kind of looping through this every time, because you're always failing, and you match all the things that are in the location. So you print them all. Oh, you see, this is like a clever way that we express a kind of a for loop, but there's no concept of loop, nor concept, I mean, there's no for statement in the Prolog language. So use this thing. So that whole thing we saw when we had the trace on, the whole process where you go from one clause to another trying to match, this process is called, in Prolog, is called backtracking. So you use either success or failure in the backtracking mechanism to control the flow of your program. So this kind of flow control, it's more implicit than really like made by imperative statements like if this, do that, or for loops. You see, you express everything with clauses. It's a completely different way of thinking about the code. It's really, for some applications, really beautiful. Actually, I'm really liking it for this text adventure. I think it fits quite nicely. But we also have another listings here, right? That I mean, between the two ones that I explained, we have another one. So this one you only get here if there is no location that there's no thing. So I mean, here we're saying we want a match of anything, because this anonymous variable means pretty much, you know, could be anything in there, and we don't care what that thing is. Anything that has the location, and here we put a not. So because we are negating this predicate, which, by the way, you see that we use another predicate, the predicate not, that you get from Prolog to negate another predicate. So by negating that predicate, you're basically saying, I only satisfy this condition if there's nothing here, right? Because there is no thing that satisfies the condition being in this location. So in that case, we actually write nothing. And then we could actually succeed here. This fail is not really needed, but I fail by consistency, and then you get to the third and final listings, and here you are satisfied. So what happens that if the location happens to have one or more things, you're gonna kind of iterate through this first clause, the number of times that you have things in the location, and then you jump here, and then you complete listings, and you're done. And if you do not have anything that is in this location, you end up matching the second condition, and then you print out nothing, because you remember here we said you see, and then if there's nothing to show here, we say you see nothing. and we're done. So that's the kind of the new thing, and we have some more stuff I want to show you, but those are kind of more of the same. Here we now have predicates for taking objects, and we check whether the object is in the current location, and if it is, then we change the location of the object to be in the inventory. And this change location, we're going to see later, is just a retract and assert in the database. Then we find the description of that object, and you say you have taken a lamp or a key. If this clause is not satisfied, it means that you cannot take the object because it's either not here or it doesn't exist. I mean, you just said get, I don't know, candle, and we don't have a candle in the game. And then we answer by saying, yeah, there's no blah, blah, blah here. There's no candle here. Or you ask for the key, but you're not in the room where the key is. Then, yeah, there's no key here. I mean, there exists a key, but not here. And drop is the opposite, right? The take is check if it's in the current location and then put it in an inventory. And drop is going to check if it's in the inventory and then put it in the here location, if it is in the inventory. And if it's not in the inventory, then you say, okay, you are not carrying that object. Change location, as I said, it's basically a retract and assert, pretty much like we did to change the here predicate. And now we have the inventory, and the inventory is, you say you are carrying, and then you just call the list things predicate that we saw passing inventory as the location. So when you are doing this as part of the look command, the look predicate, you list things that are in the location here, and inventory, the location inventory. So let's take a general look. So you see we are in an empty office, and now I actually expanded a little bit the description, and you see a lamp. And if we go to the south direction and look again, we see a key, and now we can, for instance, take the key. And now if I try to take it again, because it's not here anymore, say, yeah, there's no key here. And if I look, indeed, I see nothing. I go back north, I look, and I have a lamp here. So I could, for instance, take the lamp. And now if I check my inventory, I am carrying both the key and the lamp. And if I drop the key, oh, sorry, I forgot the parenthesis. We're not there yet. And I drop the lamp. And I look again. I have dropped them both. They are here. And you see that now we have objects and we have inventory control. We are now at a point where we can take the next step and understand how to parse user input and how to basically have a game loop that keeps asking for new commands until you satisfy the winning condition of the game. So this is very close to having a complete game. And we're going to introduce some of the more complex constructs now. And I mean, if you can understand this, then that's you can figure out everything that we are doing here. I'll try to explain the best I can. So we now, I have not, I mean, I will not show you typing all this stuff. So it's already typed. So let's just look together what's going on here. I introduced a new predicate that's the game loop, doesn't receive any incoming attributes. And that's also the goal of our program. So it means that our game, when we start our program, we call the game loop. So game loop will write the banner of the game. And then we reach this repeat thing. What the hell is this? So this is how we control flux, we control flow. So we are in a loop of sorts where we keep looping until a certain condition is met. It's a bit like a while or a do while style of control flow. But of course we do not have these constructs in Prolog, so we use repeat. And repeat is not even defined by the language. Repeat is something that we are defining here. So the idea is you define a predicate that returns success, returns yes, right? It succeeds. That's what this line does. We say, okay, I have a predicate repeat, receives no arguments. I just, I don't do anything. I just return like success. This is what happens when we pass through here. It succeeds and nothing happens. However, you can see that here we also have another repeat that implies first repeat. That implies another repeat with success. So that's what goes when we have backtracking, we land here again. So we started here on this repeat, and then we're gonna do stuff. If any moment while we are doing this stuff we fail, it means we need to backtrack. And then when we backtrack, and this repeat will be the second repeat will be found, and it will force you to do the repeat again. So in practice, what we have here is you start your repeat loop with this line, and then if you fail at any point of what succeeds the repeat, you go back to the repeat and you resume from there again. So basically we have a loop until a certain condition is not satisfied. We come keeping to this repeat. And there's only two situations where our program could actually pass through these final predicates with success. That's either we meet the end condition of the game, which is being in the world outside room, or in a certain command, that's the command quit, that's called as consequence of calling this predicate, but we're gonna get there. But what you have to keep in mind is you declare it like this, and then you put repeat here, and then you must make sure that you fail anytime you want to go back to this line and do the loop again. So what we do here is we had the banner and we print a new line. We look around, we show that text like, oh, you are in an empty office, blah, blah, blah. Then we take user input. And let's take a look at the user input. So we write to the screen a kind of prompt, and then we call this read line predicate, which you guessed is going to have the side effect of asking the user for input, and then after the user has typed something, like type a line and hit enter, the content will be this variable called string input. And then I am calling another predicate from the Turbo Prolog language called upper lower, which is basically ensuring that if this contains any upper characters, the string input contains any input characters, that string, which is another variable name, will have only lower characters. So we basically read the user input and put everything in lowercase, so we don't have to worry about case. So that will give you the string, which is the lowercase string that the user put there. And then we print another new line, and then we call this string word list predicate. So string word list, it will you give the input string, and it will give you back a list of words. And this is probably the most complex concept. The implementation of this string to word list predicate is kind of the most complicated thing we're going to see, and it's not that complicated. So first of all, we have this string to word list here, and when we declare the predicate, actually we say it takes let me find it here. So the first argument is a string, right? This is the line of command that the user typed. And what we want to do is break this and have a list of strings where every item in this list is a different word or token that the user types. So the user types go south. That's one big string, right? Word go, space character, word south. We want to turn this into a list that contains two strings, the string go and the string south. So this word list will be the output. And you see that word list is defined as word wildcard. That means this is a list of words. This is 0 or more words. That's a list. So that's how we declared it. So let's take a look at the implementation. So we are passing the string, and we have the other argument. This is a list. So a list is represented in Prolog as something between these square brackets. So for instance, this is just the comment character. So this is a comment, right? So a string, I could have something. I actually, if I type go south, I want to end with this list. And a list is indicated by the square brackets and with the elements between, commas. And these are strings, so they are between quotes. And you have this notation where if you say something like this, you say here a variable name, and here you put this bar and then another variable name, whatever. So this is the head of the list, which means the first element of the list, and this is the tail of the list, which means all the other elements. So if we had a list that contained like 1, 2, 3, in this case the head would be 1 and the tail would be a list with 2 and 3. So that division of a list between head and tail is something that we use a lot in functional programming, and when we have our Lisp videos, we're gonna talk a lot about this. Prolog has the similar construct. So you are saying here that I have a string and I have a list that has a head and a tail. I called from token. So what from token, which is another predicate of the Turbo Prolog library, what from token does is you pass a string. It will extract the head of it will break the string into tokens. It will take the first token, which is the head, and it's going to put in the variable that's in the second position of from token. I just called it head, and it's going to put the tail here and the rest. So the rest of the head and the list. It's if you have the string go south and you run from token the first time, it's going to you pass go south as the string. It's going to put the word go in the head and the south in the rest. So in this case, my example, we kind of have only 2 elements in the list, but if we had like 100 elements, we need to keep doing this until we have no rest, right? So until we take head per head, so we take one by one until we process all of the tokens. So you see we have a recursive call here. So the string word list calls itself again, but now we pass the rest as the string to be broken. and tail is now the new name of the of this list, the list that contains our outcome. And we want to fail. Why we want to fail? And by the way, this thing here, we haven't seen it yet. This is a special kind of failure. So for now, let's just you just have to understand that this, when you put this exclamation mark, it means you are failing. So because you are failing, you remember when we process a predicate and the predicate matches, it succeeds, it returns true or yes, we stop processing it. But here we want to keep processing until we are completely out of, until front token will not have anything more to process. So that's why we fail. We keep failing. And when we have nothing else to pick out, then we find in the we fall in this other version of the predicate, which no matter what's your input, you just return an empty list and success. So this gets appended to what you had. So this will return to you in the head tail argument is going to return to you the list that we want. And then you understand now that here in this string to word list, we put the string, and here we get the list of words, and then we call do, the predicate do with these words, which is a list. And then we have all these implementations of the do predicate that take different arguments. So if you match, and you see that this, Prolog is wonderful for doing parsing and for doing pattern matching because of what you see here. So this predicate says if the input of this predicate is a list that contains the word go in the first symbol go in the first position, and anything in the second position, we're going to call that anything direction, then we match here and we do whatever is in here. And if it doesn't match, then it goes to the next one. The next one, we're going to check if the command is take and then a second thing that will be the object. So if we have like more elements than just two, this will not match. If the first element is not take, it will not match, and we will go to the next one. So it's very easy. Just the predicate kind of gives you the pattern matching. But let's take a look at what they are doing individually. So the first one, which is for the go command, you need a list where the first word is go and the second is another word. And then first thing we check if the second word is a direction. And you can see that we have a new predicate direction that is basically saying these four words, north, south, east, and west, are directions. Any other word is not direction, so we're not matching. So if we got at this point, like we got here where the cursor is, it means that we have the command go direction, and the word direction is either north, south, east, or west. And then we call go to. We already had the predicate go to. And then we have this kind of failure. So if I just had fail here, like we had before, this would still work. But then what would happen is it would try to match the next do. So this exclamation mark is a special kind of failure that's called a cut and fail. So it basically says when I get here, not only I fail this kind of specific predicate that we are, like do go direction, but we also fail all the evaluation of all the other do predicates. We don't do them anymore. So which means you don't waste your time trying, because if you already had a match and then you get here inside, it means that the command is go, right? The command will not be take, it's not going to be inventory, not going to be quit, it's not going to be anything other than go, because the first word is go. But if we don't have the other conditions, like it's not a direction, then I want to not only fail, which means that I go back to that repeat thing and I do it all again, but it also means that we do not check the other do predicates, because I mean we don't care about checking them. So again, the cut is another way that we can kind of control flow in a smart way. So we're gonna, if we have a match in Go, we try to do this. If we have a match in Take, we do a similar thing, right? We try to see if the second word is an object, and there's a predicate object to do that, which we already knew, right? Basically, it's the lamp and the key. And if we call the take command and this is an object, we call the take command, which will then, the take predicate, which will then check whether the object is here and all those other things that we already have done. Same thing with drop, same thing with inventory, but inventory, it's a single word. So whenever you type inventory, the single word inventory, you fall here. And now we have a help command. And we have quit. And you see quit, it's the only one that's not failing, right? All the others, we have the cut, which makes them fail, but this one doesn't. So that one, if it's one of the two cases where we get out of the game because we don't go back to the repeat. Recall, we have the repeat and then we have predicates, and if we fail at any of the predicates, we go back to the repeat and we do it again. But if we don't, we just fall through and we end our program. Finally, I have a do at the end where it's basically accepts anything, because if we got here, it's not any of the recognized commands, so we don't know what this is, and then we'd say, what? Say what? And finally, we also have the end condition, right? And the end condition is that you if you are in the world outside, then you say, okay, congratulations, you have won the game, and you're out. Okay, so I guess we have covered it all about control loop and how we are breaking our input into tokens, and then how we are doing pattern matching to see what tokens we have, and then doing something based on it. So now let's take a look at this thing running. So now you see I'm not anymore calling the Prolog predicates. I'm really like just interacting with the game the way I want, just typing commands. So you see everything is working, but right now we are kind of stuck, right? Because in this game, once we take the key and we take the lamp, we need to be able to use the key to unlock the door that takes us to the dark room, and then light the lamp so we can see in the dark room and we can see the exit that takes us to the world outside. And adding these commands are the last step to have a complete game. And here we have the complete game. And we added a couple of things. So in the database now, not only we have the here and the location of the objects, but also the description of the rooms and the objects can change, and also the exits from rooms can change as well. And now we have a command that's called unlock door. We check if we are in the empty office, right? If here is the empty office. And then we check if the key is in the inventory, because you cannot unlock the door if you don't have the key. And then if we satisfy these conditions, we have the key and we are in the empty office and we type unlock door, then we can unlock the door. And unlocking the door actually changes the description of the empty office, because the description said there is a locked door to the east, and now we just say there's doors to the south and to the east, so it's you can go. And we add another exit from the empty office when you go east that you land in the dark room, and then you say, okay, you have unlocked the door. But if you call unlock the door in any other condition, like you don't have the key, then say, I mean, open the door with what? Or if you try to unlock the door, I mean, if we got here, it's because you have the key, but you are not in the empty office, so there's no door to unlock there. And here we have the light lamp command, which checks if the lamp is in the inventory. If it is, it changes the description of the lamp to come from just a lamp to be a lit lamp. And the dark room also changes. It's now not a dark room where you cannot see anything. It's an empty room and you see a door leading west, which is back to the empty office, or to south, which is the world outside. And then it says, okay, now you have a lit lamp. So when you get to this point, you can you can actually go outside, right? So, but if you try to light the lamp, you're not, I mean, you don't have the lamp, then of course you cannot do that. And that's all. With that, we have really a complete game that you can play through. So let's demonstrate. Let's do something even better. Let's compile this thing to an executable and then look at not in the development environment, but really like an executable that we could give anyone. So I go to Alt-C. First I have to quit the game. Then I go to Alt-C compile. I want to compile to an executable file. And I will not execute it necessarily. And now I should have a get lamp.exe. Yeah. So here's the game. So let's walk through. So you start in the empty office with the door to the south and the locked door to the east. And you see a lamp. And if you go south, you're in the stock room with a key. You take the key. And then you go north. And then you take the lamp. Then you have now the lamp and the key. And what you do now is that you unlock the door. And now that you have unlocked the door, you can go east. And once you go east, you're in the dark room, but now you cannot do anything, you don't see anything. So now we have to light the lamp. And I have now a lit lamp. And now I'm in an empty room and I see doors leading west and south. So let's go south because we haven't been there. And we have won the game. So that's it. I hope you had fun with this. I mean, I had a lot of fun. This is much more readable, I think, honestly, than even the C version of the game. This is really awesome. This is I had never programmed in Prolog, but I'm really happy I gave it a try. It's I'm not saying, I mean, it's like much better language in itself, because I don't think there is such a thing that one language is inherently better. I mean, in all aspects, something is better at something. So I think Prolog is great for pattern matching, and Prolog is great for systems that you have to, you have a series of statements about things that exist and the connections between these things, and you need to navigate easily these structures. So that's what I really loved about it, and I would definitely use it for similar things, especially the modern variants of Prolog that you don't have all that thing about declaring the predicates and the domains. You just, it's very dynamic. There's no typing. You can go and just immediately declare your predicates and play with them. But definitely, I mean, I'm adding a Prolog to my toolbox, and that has some interesting parallels with functional programming, which we will visit when we approach Lisp. So yeah, I really hope you liked it. If you do, please don't forget to subscribe so you can be notified of new videos. I would love to hear suggestions of what you think about the stuff we've done here, and what would you like to see in coming videos. So yeah, thanks for your audience.